As last class we have explained about primary consolidation, secondary consolidation, and initial consolidation. So there is a spring analogy for primary consolidation, which is explained with a diagram, which can be understood by reading the process. So, and then next comes the consolidation test, which I've given assignment, and you can refer from this notes, or you can refer from Punmia Aurora textbook. Okay, so these methods. So after this consolidation test, determination of void ratio at various load increments. Okay, the result of a consolidation test are plotted in the form of plot between void ratio and effective stress. Okay, so consolidation test, we form a graph which gives a plot between void ratio and effective stress. Therefore, it is required to determine void ratio at various load increments. So we need to determine the various void ratio at various load increments. So there are two methods. There is height of solids method. Okay, so applicable to both saturated and unsaturated soil. In this method, equivalent height of solid is determined from the dry mass of the soil. Okay, so we have equation, that is Hs is equal to Vs by A, which is Ms divided by G gamma W into 1 by A. So Hs is height of solids, Vs is volume of solids. Okay, Ms is dry mass of sample, and A is the cross sectional area of the specimen. Okay, so what do we have? E. E is volume of voids to the volume of solids, right? We can also write it as V minus Vs divided by Vs. So when we substitute it, E is equal to A into H minus A into Hs divided by A into Hs. So what do we get? So we get E is equal to H minus Hs divided by Hs. Okay, you can just substitute in your book and try it out. So where H is the total height, total thickness, this void ratio is determined from total height H and height of solid. So total height is given by H is equal to H naught plus summation of delta H. H naught is initial height and delta H is change in height. So the total thickness of sample is measured before the start of the test. At other loading stages, the thickness H is worked out from the measured thickness and difference in dial gauge. Then from external question paper point of view, they might ask question regarding like to explain any of the method or like the equations. Okay, the next method is change in void ratio method. In this method, the final void ratio ET corresponding to complete swelling condition after a load has been removed is determined from its water content using the equation. So here void ratio ET is equal to Wg. Okay, assuming where S is equal to 1, which is fully saturated. The void ratio corresponding to intermediate loading stage is determined as below. E is equal to V minus Vs by Vs, right? So V divided by Vs minus 1, we take it. V is equal to Vs 1 plus E, right? We take this to this side. So what is volume? Area into height. So Vs, A into H is equal to Vs into 1 plus E by partial differentiation, right? A into dH equal to Vs into dE, that is B. So this is equation A, equation B. So from A and B, dH by H gives is equal to dE by 1 plus E, which is delta E is equal to 1 plus E multiplied by delta S divided by H. Okay, you need to learn this equation. Okay, they might ask any of the method for 3 marks. As the void ratio ET and total height H of the sample are known at the end of the test, the void ratio at any other stage can be found from the change in thickness delta H measured by the dial gauge. Okay. Thus, the change in void ratio delta E under each pressure increment is calculated by working backwards from the known value of void ratio ET at the end of the test. Thus, delta E gives 1 plus ET multiplied by delta S divided by HT. where delta H is the change in thickness as measured with respect to the thickness HT at the end of the test. Okay. So consolidation test result gives a dial gauge reading time plot. So figure A shows the plot between dial gauge reading and time for typical loading increments. Here we have dial gauge reading and time here. Okay. So the thickness just after application of load increment is T is equal to T naught. Okay. Just after application of the load increment is T naught. T is equal to T naught is a maximum which decreases as time increases. Okay. So the decrease in rapid initially, but it is slow down as a time passes. Right. Initially increase the it goes in a speed and then slowly it decreases. There is practically no change in thickness after 24 hours. After 24 hours, there is no change. Consolidation is considered to be completed 24 hours. Here, there will be no drastic change. So, it is considered to be completed 24 hours. For sand, the change in thickness occurs very quickly and stops after a few minutes. Okay. For sand condition, the change in thickness occurs very quickly and stops after a few minutes. This is due to high permeability of sand, which allows easy flow of water. So permeability is high, hence there is easy flow of water. The plot between dial gauge reading and the time is required for determining the coefficient of consolidation, which is useful for obtaining rate of consolidation in field. Okay, the next we will be learning coefficient of consolidation. So this dial gauge reading and time is necessary for that. Okay, next one is final void ratio. Okay, effective stress plot. We have here effective stress, we have void ratio. Right. So figure B shows the plot between final void ratios EF1, F2, F3, E and comes effective stress sigma 1, sigma 2, sigma 3. Okay, for load moments, load increments 1, 2, 3. As sand is relatively less compressible, change in change in void ratio is small. Okay, so as it is relatively less compressible, so there will be change in void ratio is small. This plot is required for determining of magnitude of consolidation segment in field. Okay, next is final void ratio log log city stress plot. Okay, sigma plot. Okay, it is more common to plot the result on a semi-log graph in which the final void ratio is plotted on natural scale and effective stress is on log scale. The plot is a straight line for normally consolidated clay. So for a clay, it is a straight line. Okay. Unloading, reloading plot. Next comes. Okay, here the curve AB here indicates the decrease in void ratio with an increase in effective stress. Right, here there is void ratio, here is effective stress. With an increase in it is the loading curve. Okay, it is taken as a loading curve. After sample reaches equilibrium at effective stress, okay, 2 at B, the pressure is reduced and the sample is allowed to take up water and swell. Okay, here the pressure is reduced and the sample takes up the water and swell. Okay, curve BE. Okay, BEC. Sorry, BEC is unloading curve. Expansion curve or the swelling curve. Okay, unloading. Okay, so if sample is reloaded at C, the recompression curve CFD is obtained. Okay, if it is reloaded, so then CFD is obtained here. As load approaches maximum value previously applied, as load approaches maximum value previously applied corresponding to B, okay, then is reversal of curvature and plot DG continues as an extension of first loading curve.